switch gears off kind of ever more increasing sophistication of implementation techniques and look at a completely different way of what we're building. VMs, so this is a technique that's been developed by my group in Oracle Labs and has some interesting results and momentum, and this is what you're going to be using for your next exercise. Next week is Thanksgiving, so no lecture. It'll be 2 weeks to the next one, and then the last 2 lectures will be on concurrency techniques and tools. I have another guest speaker coming in on the 11th. Okay, so here's a graph I put together a while ago. It might be more than a year ago. It might be nearer 2 years now, in which I took the data on this website called the Computer Language Benchmarks Game. You've probably seen it if you're a programming language guy. It used to be called the Language Shootout website, and basically it's a bunch of applications that have been recoded in a very large number of languages, and then performance data have been submitted against them. And what I did was I took a collection of languages from, mostly from like the TOB top 20 languages list, and plotted the data for the performance of, the best performance of each of those language implementation pairs, and normalized them to see which I took as, kind of unity. Pinch of salt, right? Don't, it's called a game for a reason. You shouldn't take stuff like this very seriously because, for a start, a lot of these programs are completely out of the normal domain of usage of some of the languages. The applications, for example, written in R here are like, you would never do these things in R, right? No one in their right mind would do them. So, it has to be taken with a very large grain of salt. But nonetheless, there is some kernel of truth in this. When you plot the performance data on a logarithmic scale, not linear scale, you get a pretty big spread of performance. You get a bunch of languages with pretty decent performance. You get JavaScript, which currently sits in the middle, although my guess is if I redid this graph now it would be a lot better. And then you get, broadly speaking, what I would describe as the scripting languages.
What's the blue?
Sorry?
What's the blue? Second from the right?
Smalltalk.
Oh.
Smalltalk. So that was the best of the Smalltalk results I could find. Now again, these numbers are old. Don't take it, don't use it as validation that your pet language is the best or the worst, or your friends is the worst, or whatever. It's
what's the order? Why it's not from the best to the worst? It's like up and down.
It's not ordered. It's just a random selection.
Okay.
Okay, and all I did really was make sure that sort of the good ones were at the left, and then over here it's kind of all just spread out.
Is that paraphrase?
Keynote.
It's not enough.
But it's as you can see, it's a big spread, and there's this group, and then these.
So R is the worst.
Which?
Of these, by far, yeah, like an order of magnitude worse on this benchmark set than all the other languages, which are already pretty bad.
What implementations of Java and JavaScript for these do you?
I'd have to go look at the website, but I picked the best numbers for each particular implementation at the time. But like I said, they're old, so it's old data.
But do we also have like the abundancy of these? Like in my eyes, is that R is one of the most widely used language in like statistics and data science.
Yeah, so I mean, this number is highly suspect because the applications that are in the suite are not statistical in any way, and they don't leverage the power of like the statistical library at all because they don't do statistics.
Right.
So a lot of this is due to the fact that in real use it would not feel this bad. It would feel this bad, right? Because this is a sense of if you write imperative loopy code in R, just how bad it is, and it's really bad. It's really bad. This is the GNU R implementation, basically the only one that's compatible with itself. But even if you use the power, you're not going to get super high performance if you stay within the language. The reason R is widely used is because people call primitives that are expressed in C and Fortran,
Right.
and those run, of course, fast. So there are bulk operations that are predefined run fast, but that's, if you're writing a new piece of program and it doesn't use one of those things, this is where you're going to live, right? You're going to live in this band. You're not going to live down there. You know. I'm sorry?
No serious R user will write a program without using externalities.
Yeah, no, actually, I've looked into this. And in fact, if you look at the way it's used fairly widely, people will develop new stuff using R, you know, like a new technique for which there isn't a kernel implementation. And then when they figure they've got something valuable, then they recode it in C or C++.
It's more like a prototype language.
Yeah, yeah. And so what that's saying is, you know, it's painful, it's productive to begin with, but the performance is poor. But once you've got something you want, then when you recode it, you can get the performance. But it's, you know, the performance is not good.
Did anyone look into MATLAB?
I think there are MATLAB benchmarks, but I didn't pull those out. I don't think there are many different implementations. Yeah. Go look at the website. It's kind of fun to browse around. You can slice and dice the data in all sorts of different ways. Anyway, well, why is this? So I believe it's because the flow in building implementations historically has been kind of this. You have some idea for a language, you build a parser, you build an AST interpreter, you fiddle with the semantics, you sort of get it to the point where you think you have a reasonable definition of your language, and of course it's pretty slow. As you've seen, AST interpreters are pretty slow. So then you go off and you start devising, you know, building a real VM, usually in C or C++. You spend a lot of time implementing all the runtime. You might throw out the conservative collector and build one that's exact, things like that. You know, you get some adoption, people start using it, and as soon as they use it, they say, we love your language, but it's really slow. Can you make it faster? So then maybe you go off and do, you know, what we did in phase 2 of the exercises, define a bytecode format, build a bytecode interpreter, all of that machinery. And as you see, it got faster, but it's still pretty bad. And then, you know, if you want real performance, you start doing what you've recently been doing, which is write a JIT compiler, improve the garbage collector. You're still a good ways off C or Java at this point. And if you want to take that last step and get into that bottom band, well then, you know, you break out your wallet, you hire half a dozen or 10 or maybe 20 rocket scientists like Lars, and burn some tens of millions of dollars, and you end up with something that's pretty good. But, you know, the reality is most give up there, because that's kind of where the knee of the curve is, right, in difficulty. It sort of gets much harder at that point, as you've seen. How hard? Here are some estimates based on what I've observed at Sun and at Oracle in implementation. Okay, so you start off with something like a Blue Book standard interpreter, like the interpreter you had, and it's kind of, you know, a couple of months' work, not that hard. You can get something pretty decent. When you get into a simple JIT for a real language, you know, Fini, I hope no one will dispute, is not a real language. It doesn't have any of the complexity of real languages. But if you go down that path, now you're talking about a year's effort maybe to do a decent JIT that's maintainable. The self system, you know, gets you another, this is again another logarithmic chart, you know, gets you another several-fold speed up at the cost of maybe 10x in effort. And if you want to get that asymptotically disappearing performance, then the effort kind of goes up without bound. My guess is hotspot, it's probably well over 100 years of efforts going into the hotspot now. It's probably in the hundreds. So another way of looking at that is, so that's where the scripting languages lie, lines of code. And hotspot, I think, is around 3 million now. You can do sort of a decent, reasonable performing VM in a couple of 100,000 lines of C++ for a simple language, but it rapidly gets complex. So I think that's why we don't have a whole bunch of high-performance VMs for these languages. First, there aren't a lot of people who can do this. And second, who wants to expend all this effort? Who's going to pay for all that effort? So, you know, the problem is each language needs its own implementation. That's the way it's been done historically, that we don't really share much from one language to the other. You know, you can try doing the one language on top of another language's VM trick, stacking them up, but that's kind of mostly not proven very successful. You either end up with something that doesn't perform well, or has terrible complexity, or isn't quite as compatible as the original implementation, or some mixture of those things. You know, and if you go down that path, you can get sort of decent performance, but at absurd levels of complexity. So if you look at JRuby, which is what I'm somewhat familiar with, JRuby is the Ruby built on top of Java, runs on top of a standard JVM. The peak performance is pretty good. It's quite a lot faster than the C interpreter that's available for Ruby, sort of order 10x, not bad. But if you compare it with the same code written and expressed in Java running on the same VM, it's probably 5 to 10x off that. It's quite a long way off where you really think the performance should be. You know, if you compare it with, say, the well-tuned Smalltalk VMs of the past, or the well-tuned Self VM, you know, it's way off that kind of level of performance, even though it's got a much more sophisticated VM underneath it, namely something like Hotspot. And what's more, it's massively complex because it's trying to work around all of the assumptions of Java that are built into the underlying Java implementation. So JRuby is like a couple of million lines of Java code. It's big. Now, a fair amount of that is library, but there's also a fair amount of code in there that tries to, in effect, generate very special bytecode that's known to run reasonably well and not do it in the sort of straightforward and obvious manner. So it has its own dynamic compiler generating bytecode, for example, in addition to the one that's in the VM. And that's kind of a sign that something's not quite right. It was also probably the biggest driving force between the biggest sort of semantic extension to the JVM in recent history, which was the addition of the invoke dynamic bytecode, which unfortunately we didn't have time to go into before. Invoke dynamic is a way of invoking kind of arbitrary lookup in the JVM. You can't do that at the Java level, so it's not for Java, although it's been reused in the Lambda stuff. But it's really there for dynamic languages. And so, you know, a lot of effort was put into specifying this and developing it and putting it in the JVM. And the speed up was very modest, like, you know, 2x at best. Maybe less than that, I think. So it's still a long way off where you'd really like it to be. And I have kind of a strawman argument for, you know, this is never going to work, which is you probably want to implement both static and dynamic languages. So suppose you have a dynamic language and a static language, and one of them you already have a high-performance VM on, then there's always going to be a mismatch between those two. If you put a static language at the base, well, it won't have support for all the stuff we need to make dynamic languages go fast. Tagging and dynamic layouts and open-ended dispatch and all of that. Inbound dynamics kind of a step in that direction from Java, but it's clear from the history of invoke dynamic that there's a lot more needed if you're going to run dynamic languages on top of a stock JVM through the Java bytecode set. And if you do it the other way, you end up with a similar mismatch that you don't have in the dynamic languages support for machine level types and vtable dispatch and stuff like that. I've dabbled with this. In the Self project, we built a very early implementation of Java by translating Java bytecode into Self bytecode. And it was faster for its time, but that was before Hotspot and similar VMs appeared. And you know, I don't think it'll ever compete with something like Hotspot. So, one of the problems here is that, you know, we don't reuse things, and one of the difficulties is if you look at the high-performance VMs that are out there, they're generally not very well modularized. You don't have big pieces that you can just lift out and reuse somewhere else because the components tend to be deeply entangled with each other. Many have tried to put interfaces in, and there's been some level of success in putting interfaces between parts of the VM, but even now, if you look at most of the high-performance ones, you get issues that cut across all of the different modules. And you know, if you're working on GC, you have to know something about what the compiler does. If you add some new barrier, you have to go and change the compiler. If you add a layout, you have to go and change both. It tends to be very deeply entangled because it's sort of a holistic attempt to squeeze the last drop of performance out of the underlying machine. And to do that, you really have to know about everything. You can't just kind of close one off from the other. At least, if you can, no one's figured out how yet. Optimizing compilation is really interesting because that tends to be the single most complex part of the VM. An optimizing compiler is sort of ferociously complex, even compared to the GCs that we've seen. And they tend to be very language specific. But the funny part is that most of an optimizing compiler isn't language specific. Most of what's on the inside is actually fairly language independent. And so the interesting question is, if you took an optimizing compiler, if you started with the core of the optimization framework and the IR, how would you get to a system in which you had a reusable language-independent core with some language-dependent parts, probably language-dependent optimizations? You'd need front ends for each language you were going to implement. You'd have to somehow optimize for the behaviors that you discovered at runtime, because as we've seen, it's all the techniques here are all about runtime mechanisms and finding out behaviors that aren't manifest in the static code. So you'd have to have some way of doing that in a way that was language specific and yet somehow reusable. And then you have to pick a language to write this stuff in. What would that language look like? Is it C? I imagine by now you're probably sick of C. And I'm guessing none of you are going to answer C as that language. But what would it be if it's not C? So what I'm going to talk about for the rest of today is one pass at this that we are making at Oracle Labs. So we have a system that's been under development now for 4 years, I think now, building on some of the earlier work that we did on things like Maxine. And we have an approach that tries to address this and produce a framework in which the bulk of the complexity can be reused from language to language, but you can still write independent language front ends and give language semantics and get pretty good performance out of the whole thing. Comparable to what you'd get if you spent all that time building a custom VM for that one language alone. So I managed to avoid logos all this time. Now you get the Oracle logoed slides. So this is like all our technology coming up, but hopefully it'll be interesting. So where do we start from? Well, we go back to AST interpretation. You remember this slide, taken literally from the first slide deck? Two things about ASTs: they're slow to interpret, but they're easy to reason and write and reason about. So that would be a great way of specifying a language's semantics. If you could write an AST interpreter but have it run fast, that would be an ideal situation. So what do we need to make something run fast? Specifically, we're assuming that to make it run fast, we need to compile it. We need to generate good code for constructs that are in the original program. And so what do we need to do that? We need, obviously, the program itself, because you can't compile an interpreter and get good performance. You need to start with the original program somehow. You need to have an understanding of what each element of the language that program expresses means in an executable form. And you need to combine these things, so elements of the program, with their semantics, and then generate code for them. So this is just, how do we get code? So remember the simple AST interpreter that we started with that was just interpreting expressions? This is lifted from that slide. So we've got the dispatch on an AST node, and we're just going to evaluate based on what kind of node we've got, and we recurse down the tree. So how do we turn that into a compiler? Well, suppose we have our favorite expression from early on, and we have our interpreter here. What we can do is we can do a an abstract interpretation of this, executing the parts of the structure that are given by the fact that we have a known program fragment, right? So we know we're trying to compile this program fragment, so we know the tree shape. So we can do the tree walk at compile time, but we can't evaluate all of the expressions at compile time because these are dynamic things dependent on runtime values. But we can pull them out and combine them to make a compilable expression. So as a sketch, let's start with the assignment we're assigning to B. We can take the definition of an assignment, which is here, just pulling out, evaluating the right-hand side and assigning to a corresponding variable. Well, we know the variable, so we can fill that part in, but we don't know the right-hand side. The way we do that now is we abstractly interpret down here, so we know the structure of the tree and we can recurse down. So now we look at the right-hand side, we see that there's a plus with two further recursive evaluations of the tree part. So we can fill the plus in and then recurse down. And so on, we work our way down the tree, pulling out the piece of code, filling in the details as far as we can. Constants are just constants. Variable becomes a variable lookup. Until we have something which is pretty good code for the original expression, right? The interpretation is gone, and we've got the semantics as we would want to compile it. That's not a new idea. That's been around a long time. The idea is to take a language interpreter and a thing called a partial evaluator, which evaluates what it can based on the structure that's known at the time of evaluation and leaves the remainder for evaluation later. And that's one way of taking an interpreter and making it into a compiler. You combine the interpreter with a partial evaluator and you get a compiler. And to compile a different language, we just need a new interpreter in the scheme, right? We don't need a compiler for the original, for the guest language. We need a compiler for the language that the interpreter is written in, a partial evaluator for the language that the interpreter is written in. So that's been known, since the 70s. There's a paper from 1971 by a Japanese professor, Fujimura, who came up with a formalism that describes that. And it's been around a long time, but it actually hasn't resulted in particularly efficient language implementations. Certainly not dynamic language implementations. Well, why is that? The problem is when we look at partially evaluating a dynamic language interpreter, life is much worse. So the previous thing was very simple because we had only one type. When we get into dynamic stacks and tagging and all of that stuff, so this is the code lifted from the slide when we had a tagged scheme for the stack. Now if we imagine substituting that in on one side of a plus, and substituting something else in on the other side of the plus, the resulting code is not going to be much more efficient than it was when we were interpreting. We're going to remove the interpretation loop, but that's more or less about all. What we need is some way of pruning out the part of this that isn't useful. So what we need is to generate good code for a user program. And that requires what we had before, the semantics and the user program, but we also need to be able to gather information at runtime as to what the program is actually doing, use that as the predictor of the future, and use that to optimize how we select from the interpreter what goes into the compiled code. So we're going to combine the semantics of each element of the program in the same way that I just showed you, but we're also going to drive the way we combine it based on usage information gathered, say, through an interpretation warm-up period. And that's how we're going to generate the code that we're going to compile, and we're going to use the de-optimization trick to back out when we get that wrong. So de-optimization is the big hammer here to get us out. So the AST interpreter gives us the semantics of each language element by definition, because that's what its job is. We do profiling and specialization within the AST to gather hotspot and type information that's needed for the code generation. And then the final stage, the partial evaluator / compiler, is something that looks not just at the interpreter code, but it also looks at the structure of the AST, the original program to drive code generation, to guide how it's going to generate code. Combines all of those together. Okay, so how do we do the specialization? What's that all about? We want to gather profile data during AST interpretation, and we want to be able to get type information, but it would be good if we did that without having the explicit multi-way type dispatch in every interpretation. We rely on history to predict the future. So imagine this little piece of pseudocode for an add operation in a dynamic language. So in this add operation, we can add integers, we can put a plus between strings, which concatenates the strings, or there's some user-defined thing that we can call. And this is how you'd write it in a conventional interpreter. You do the explicit type dispatch between them. But what we're going to do is we're going to break that node with this associated semantics into different states. One for the state where we're doing integer addition, one for where we're doing string addition, and one for the generic case. And we're going to replace this generic example with the specific example that we've discovered to be the appropriate one when we've run this particular node in the past. We're going to rely on that and optimize the node-to-node communication to make the interpretation quicker, and as a side effect, gather the type information we need. So imagine again, we have this language, it has the two types, int and string, and it has some generic case for this addition. And we have the state that we start in, which is we see an addition node, but we've never executed, so we don't know what state it is. What we're going to do is when we execute that for the first time, if the arguments are ints, we're going to specialize it into as an int addition. If we see string arguments, we'll specialize it as a string concatenation. And if we ever are in one of these states and we see the other one, it's a mixed type, then we're going to fall back to the generic case and say, okay, it's neither ints nor strings, it's both, so we have to cope with both. How does this work in the tree itself? So here's the same expression I had earlier. Assume our A is storing an integer. So because that's already been assigned to, it knows it has an integer, and the integers, of course, know they're integers. So they're blue, but the interior nodes, having never been executed, they're light gray, which means uninitialized, unspecialized. Okay, so an eval comes into this tree to evaluate itself. The eval, of course, gets passed down the tree. It evaluates the 2, which gives us, a boxed or a tagged, a generic representation of 2 back. It evaluates the A on the right, and that gives us a similar, boxed or tagged representation of the value of that variable back. And now the multiplication node can say, oh, I got integers from both of my descendants, which means I'm doing integer multiplication. I'm going to change myself into a multiplication node that assumes now, in future, I'm always going to do integer multiplications. I'll optimize that case, and I'll pessimize the other cases. Okay, that then returns its result back, and plus does the same thing now. It gets the 6 it got back and the 1 it gets back from here, and it says, oh, those were integers. I'm going to be an integer addition node from now on, and it returns its number. Now the next time we come in and execute here, assume we get the same top level message come in, eval yourself. The integer plus node says now, oh, I'm a plus node, so I'm an integer plus node, so my children are I'm expecting them to give me int back. So I'm going to do a different evaluation operation now, which assumes the type is an integer. So it can give it me back unboxed. It doesn't have to tag it or box it, it can just give me a raw int back, because that's what I'm expecting. If it turns out to be something else, it has to signal out of band somehow that assumption was wrong. But assume that all the assumptions are correct. It similarly passes on the eval int to its children. The 2 can just return an unboxed 2 now. The A can return an unboxed 3. The multiplication just does a straightforward integer multiplication and returns that, and so And we've done the evaluation of the expression now using no additional conversion operations at all the intermediate stages. Right? We're not boxing and unboxing in every, or tagging and untagging. We're just trucking in regular raw ends. So every time we do this now, it should be faster, plus we know by the fact that this is coloured blue, that the fact that we've never seen anything other than an int here.
Question?
Yeah.
So where are the guards inserted? Like where do you check if it's
I'll show you. The next one. So assume we go off and we do something else, and in the meantime we assign a string to A, right? So now A is no longer an integer. We fire in our eval message. This guy says, oh, I'm an int plus, do an eval int. That guy says, I'm an int multiply, do an eval int. The 2 responds okie dokie and gives the 2 back, but the A now says, can't do that, I'm not an int. It has to respond out of band. So, for example, it throws an exception maybe and says, I am an X, it's not an int, do something different. When this guy handles the exception, what he does is he replaces himself now with a generic node. He says, okay, I used to be an int node, but I've seen something that's not an int. I can't do int stuff anymore. I'm going to replace this node with a generic node that's going to handle it in the standard boxed or tagged manner. And it replies with the unexpected result back, because remember, the plus asks for an int, and it can't give it an int back, because let's assume now in our language 2 times the string x is x followed by x. Silly language, but whatever. So it replies with the exception, and the plus has to similarly convert itself to the generic case, finish off its evaluation. Note that when it asked for this guy, it asked not for an int, but for a generic thing, and return the boxed example back. And now we have a case where we know from the colours of the nodes that this has seen both strings and ints. So in pseudocode, the way this looks is that your node class, every node has to know its parent because it has to be able to replace itself in the tree. So the tree is fully connected up and down. A binary node then is going to have 2 sub-expressions for the left and right child, and it's going to respond to 3 different eval requests. One, which is the generic eval, evaluate yourself and give me back some kind of boxed or tagged representation of the result. The one that says, please evaluate yourself on the assumption you're an integer and give me back an int. And if you can't give me an int, then tell me by throwing an exception. And similarly for string. And then we're going to have subtypes of the add node for each of the different states that we're in. So the uninitialized one is going to just call its children and figure out how to replace itself with the appropriate type. The integer add node is going to implement the eval int and the exception, but if it gets asked the generic thing, it will do that too. I've elided that. The string implements the string concatenation, and the generic one does whatever is the generic case, calls the user-defined plus or whatever is the language specifies. What we're going to do now is instantiate the add node with the uninitialized one. When it sees ints, it's going to replace itself with the int add. When that sees a string, it's going to replace itself with a generic one. And by that way, the tree will color itself with the types that it's seeing, or the union, as it sees multiple types. So here's what the uninitialized add node eval would look like. Go eval your left side, go eval your right side. If we have 2 integers on those, then we're going to replace ourselves with an int. If we have 2 strings, we're going to replace ourselves with a string. Otherwise, we replace ourselves with a generic. Say you're allowed to have 2 times a string here, and that's legal. That's the replacement case. So each node has to have a state diagram that works its way through this internal type system, transitioning from one state to another. And when it makes the transition, say the multiply here, when it specializes itself to the int case, it makes a new node of the appropriate class, the int add node, and that gets spliced into the tree now. here's what the code for eval int in the int add node looks like. So this is the case where we're going to do the left and the right evaluations, but we're going to catch an exception if either of those doesn't give us an int. So, because remember, eval int, the signature is give me back an int. It can't give you back anything else in the normal functional return. Anything else has to be communicated out of band using the exception. So this is going to throw an exception if it can't give me an int. And I'll rewrite myself by evaluating the right-hand side and putting that in there. But this is a generic eval now, it's not an eval int. Similarly, when I do the right side, well, I already have the left side that's stored in A, so I can pass that on to the rewrite. But I'll have to do a rewrite of the node if I get something different. And if I don't get either of those, then I can do the addition. And the important part here is, when this is compiled and speculated on, all that's left is the eval, and the add. Right? Everything else, the compiler is going to remove in the speculation. So the ASTs, imagine now we have an AST for a whole method, connecting all the expressions and the statements. Do you want me to give you a call later when I get to the last part?
Sure.
Do you have a number?
Yeah. Yeah. Here it is. Okay. 415 810 3614.
Great.
Just text me.
Yeah, we take a break after this section. I can call and text that.
Yeah, that's good.
So we have an AST for something like a method that's connects all of these nodes with their subspecializers. We're going to decorate the node with counters that are counting whenever we interpret through a certain node. And that's going to give us the profile information, the hotness of the tree. When we get a hot node, typically a hot method, we're going to invoke a compiler. And the compiler is going to walk the AST. The compiler knows about ASTs. It's not a compiler of the source of the interpreter. It's a compiler of the source of the interpreter and the AST. So the tree structure is known by the compiler. So it walks the AST, and it can connect each AST node to the corresponding eval or specialized eval for that node. And it knows the types of each node. It can see that because it sees the specializations. And it uses that profile information to guide the inlining. So when it sees an int add node, it's going to inline the eval ints of the children. It's not going to inline any other evals because it knows that guy's been executing ints. The only one that matters is the int children. And it's going to do that as far as it can through the tree. Where exceptions get thrown, so where the code is that does a test, a type test, say in the actual leaf. So when the lookup of the variable has been compiled and specialized, that will have to do a type test to say, well, do I really contain an int? If it doesn't contain an int, it throws the exception, and the exception results in the whole tree being de-optimized and re-evaluated in the interpreter. So the compilation, here's an example. Here's the code for the int add node. Suppose we're compiling this tree starting with a row. When the compiler sees that, it says, okay, I got a plus, which means I'm going to evaluate this method because it's a blue plus, it's the int plus. When it evaluates, it says, okay, this is an int plus, I'm going to discard all of this boilerplate around it. That's just going to be stuff that triggers or responds to de-optimization, and just get left with the evaluations of the children. And then when it goes through the children, it will go through their code and get successively build up the expressions in a tree form, just the same way as I showed you earlier. When it combines all of that lot, the try should have been removed, you end up with 2, get B, or do a multiply, add an add. Okay, that's the basic idea. Questions?
Can you go back one slide?
Yeah.
Can you show how do you read the throw rewrite expression? How do you read that?
So that says the evaluation of the left child did not return an int. It could not. it gave us back the result it could return that's boxed inside this exception. What I need to do is I need to rewrite myself, so you can think of this as this dot rewrite on the node. The node is going to clone itself into some other type based on the type of the result it got here and the type of the result it gets there. It's going to clone itself into the appropriate specific subflavor of, in this case, add, appropriate for those types. And it's going to splice itself into the tree here, replacing these links with links to the new one. So that's what triggers the rewrite of the node in the tree with a different specialization. And similarly for this case.
So I'm guessing
And the throw is because we have to communicate that result up to our caller because we can't return it in. Yeah.
So I'm guessing the framework is monitoring the profiling information and then regenerating code with eval_int or eval string based on.
I'll get to that. It's actually all generated ahead of time. All of these variants are generated ahead of time. There's no level at this level. It's not generated at runtime. It's generated at build time. And the dynamic compiler is selecting paths through this code to generate machine code for, and everything that's off that path is a de-optimization.
Oh, okay.
That's where we're headed. But I'll go through that in
So
detail.
the reason I asked this question was, would it make sense to, instead of having code that, for example, does left_child.eval_int, you have a generic eval, but you use a fancy class hierarchy and have dynamic dispatch. But because the code is being cloned, the inline caching of the generated code itself is able to specialize.
You could do that, but this is more direct. It says
Okay.
exactly, I know I need an in, I'm just going to go for an in. That's the assumption in the int node. So it doesn't have to do a dispatch. It's encoded that assumption, so it can now rely on that assumption in the way it operates. And that's useful because when the partial evaluator partially evaluates this, it doesn't have to do another level of partial evaluation to take a generic eval here, examine an inline cache and resolve all of that stuff. It can just look at the source, right, and say, oh, this is an int. I'm just going to call the int variant. So it's an extra level of indirection which wouldn't do any harm, but it would cost you a little bit of performance and complexity, which is why it's not.
Yeah, but the thing is, because then you could lift the profiling part and you wouldn't have to have the framework do the profiling. The runtime itself would be doing the profiling.
The runtime is doing the profiling anyway. You don't write this. This is just to give you an idea of what's at the bottom.
Okay.
You're not going to write this because, as you can see, if you imagine implementing a plus this way, we've got 4 versions of this with all this boilerplate. You'd go mad typing in the code, right? We've got masses of code here for not much functionality. It's really just a big state machine. Okay, so how are we going to implement this? We're going to implement it in a language that can describe machine types because that's what we want to talk about in our implementation. We want to map the original language into some kind of machine types that we know are efficiently handled. We want to have some way of having exception paths for unexpected types. I mean, I sketched this out in Java, but it doesn't have to be Java, it could be something else. But you do need this out-of-band communication to communicate the fact when you've got a type mismatch. You need something that hopefully is going to generate efficient code for you at the end, and you need the tools which I'm going to describe for the next section, which save you from having to write all of this boilerplate stuff. You write something much more high-level and declarative, and it's going to generate all this stuff. Well, there isn't really an existing language that does all of this, right? It's what we're really looking for is a DSL for building VMs in or building interpreters. But we've got, by a series of happy coincidences, a way of doing this without actually having to invent a completely new language and build a tool chain around it. It turns out that if you take Java, you add the standard Java annotation mechanism, use that, you add compiler directives. And remember, we're implementing our own compiler, so we can ascribe any semantics we like to any element of this program. We don't have to follow standard Java semantic. We can do something different, and in particular, we can come up with things which tell the compiler stuff, but when you run them in a normal VM, they're not. So we can add compiler directives. So the combination of all of those three, it turns out, is sufficient to get us what we want without implementing a whole new language. But you could, if you wanted, implement a whole new language, or you could take this DSL and you could embed it in some other language that's capable of having this DSLs embedded in it and use that instead. So the resulting artifact is called the truffle DSL, and one of the things you're going to be reading in the next week is the paper describing this DSL. Now, I think I probably need to, who's familiar with annotations in Java? I'm guessing, okay, sprinkling, but not many. All right. So you don't need to know much because you're not implementing the annotations, you're just using them. But the key thing is that since I think 1.5 or 1.6, there's this annotation mechanism available where before certain language elements, mainly classes and methods, you can put one of these annotations that begins with an at. And the annotation has a name and it has optionally some parameterized list. And the stuff that you can put in the parameterized list is pretty flexible. There's all kinds of Java expressions that you can put in there. And you put this in, and your standard compiler says, you know, I don't know what that is, I'm just going to stick it in the AST and ignore it. But if you run Java C with an optional flag called an annotation processor, which is a Java program you can write, the annotation processor is called in the middle of the compile, and it says, okay, I got this tree, here's the API, you go do stuff with it. And the annotation processor can then go in, look at these annotations, look at Java C's syntax tree, generate some more tree, and hand it all back to Java C and say, okay, I'm done, go compile this. And so those annotations can turn into kind of arbitrary stuff that's entirely under your control, and that's what this system relies on. So the flow, when we're using Truffle, is we start with Java code with these known specifications. We use the annotations, and there's an annotation processor available for this. We call Java C, whether it's the standard command line thing or one embedded in an IDE, it should all do the same stuff because this is all part of the standard Java definition. So that compiler starts compiling your stuff. It comes across the annotations, assuming you've told it to use the annotation processor, it's going to call the annotation processor. That's going to look at all your annotations, it's going to generate some source code and hand it off here, and the compiler's going to compile that to, and out pops the thing that you're going to run. So all of this processing is done at build time. None of it is taking place while your interpreter is running. Nothing. It's all done at build time. In this particular system, it actually generates source, and it'll drop that source into files, and you can look at the source. And in fact, you're going to have to look at the source if you do single stepping, because that's what you're going to see. You're not going to see your code. You're going to see the output of the annotation processor, which has all these extra classes and nodes and transitions that you specify, but you didn't directly write. Okay, so on to the nitty-gritty. So you'll find when you come to do this, there's a package hierarchy under com.oracle.truffle, which contains the framework and the APIs. Node is the base of all of this. So when you define your AST, you have to inherit directly or indirectly from Node. That's what the compiler is looking for when it compiles to figure out what your AST is. It wants instances of Node or subclasses thereof. So you inherit from that. Node provides some structure for you and some utility stuff. So it knows how to manage tree structures. It knows how to navigate up and down the hierarchy. For example, the parent is defined in Node. You don't have to define that. It knows how to do copying and replacement. It implements the rewrite methods and all of that stuff. And it also gives a placeholder for linking nodes in the tree back to the original source text that they were derived from. So when you create a node, you can say, okay, this represents, lines 4 to 5 of file blah. That's where the original source was. And the tool chain after that can use that to show you the source when it needs to. So you inherit and you use all of this stuff. You make subclasses that define the behavior of your specific nodes. And when you build an AST, there's a distinguished node which is at the top of the AST called a root node. And that has to be a subclass of a root node. And a root node provides extra functionality above and beyond node, which we'll get to. The next thing you do is you specify in Java the implementation types for your guest language. So how you are going to represent the data in your program. And you use this annotation type system, which you give the name of a couple of, you can put lots of classes in here, and the order is important, as you'll see it matches in a certain order. So these are the things that are going to implement the values in your interpreter, the representation of your guest language. And you can also, along with this, specify checks and casts that can be used by the DSL processors to say, is this of one of these types, or how do I coerce from one type to another? So for example, if your language has automatic conversions from ints to strings, you can supply a conversion that matches that, and the annotation processor will, when it needs a string, if it only sees an int, it will call your conversion thing to do the conversion. This type system, you put this in a file, you typically stick it in a Java file and just import it into all of the other places that you're going to need it. There's a slightly more complex mechanism if that turns out to be inconvenient, but I'm not going to go into that detail. Oh, and by the way, a thing I should say is the example code this far, the stuff that I gave you, was not using the actual names. The names were simplified. So don't start lifting code from the earlier slides and think it's going to work. But from here on out, it should be fairly accurate. Okay, so you've got a bunch of nodes, you've built a hierarchy representing your AST. You need structure in your AST. You have to describe the tree structure. And the way you do that is in the simple way as you would in any object-oriented language. You have members that are node type members of the particular node. So for example, if I'm defining a node for binary operators, I obviously need a left and a right. Each of those is going to be some kind of expression. But to make the DSL processor know that these are children nodes, you stick this annotation in front of them, @child. And that says, when you're navigating this AST, these are the things you go down to find more AST. If you put other stuff in here, which you can do, it won't try processing those. It will try inlining through. So when it sees a child, it's going to say, I see a child. That should have eval methods or their equivalent, as you'll see. Those are the things I'm going to look up and try and inline and match types and process and do all the state transitions. Everything else is just stuff that you need for the node. There's a slightly different form in the case where the DSL processor is going to generate everything that you need. So if you don't actually need to mention, in many cases you can get away with just writing declarative pieces of DSL and no methods in the class. They're all generated. If that's the case, then you can use the slightly simpler form. It generates the fields, it generates the getters, it generates the setters, the types, the coercions, everything. So that's just you'll probably see that in the example, which is why I mentioned it. Okay, so how do you specify specializations? So you don't have to write any of the subclass definitions at all. What you do is you put in the methods for the node-specific behavior, and you break them out by type. So an add node is going to have the integer case, and the integer case is going to just look like an int method that takes 2 ints and returns an int. And it does the obvious thing here, and it's preceded with the annotation specialization. And what that says, it's going to take this and build that graph and all the transitions and insert this as one of the nodes in the graph. The specialization for string is going to be a little bit more complex. So when you call int add, both of the operands have to be ints. and it will only call this specialization when both are ends. But you can provide your own guard for a specialization. In this case, we have to, because let's assume in this language we're allowed to do plus between string and anything, and it will, convert the other guy to a string before it does the concatenation. So in this case, we have to provide our own guard here, and the guard is just a fragment of Java, and here's the corresponding method for what it's going to execute, which just says, okay, is one or the other a string? If either of them is a string, this is an eligible specialization. So this method will only get called because this guard has returned true. And when it does get called, everything's boxed up. It's in the generic form, right? And it's going to do toString on the left and the right and do the string concatenation. One interesting trick here, and we'll go into some of these a bit later, is you can give hints to the compiler as to where to stop inlining. String concatenation probably isn't that performance critical. You probably don't want to bother inlining through this. You want to call it, but you don't want to inline it. And so you can put this annotation called truffle boundary before it, and that at runtime, when it's compiling, it will get to this and say, okay, I'm not going to inline this, I'm just going to call it. So you go through this, try and imagine doing this for a whole bunch of stuff, and you're going to have it's going to spit out a big glob of Java code, which is going to be an interpreter for your language with all of these transitions and specializations in it. You can take that and you can run it on a stock Java VM and it will run just fine. Dog slow, but it will do the right thing. If you run it on the special VM with the special compiler in, it's going to look into all of these specializations and start doing compilation knowledgeable about the structure. So the processor is going to take your thing, expand it all out to generate all the subclasses and everything. And then when the compiler runs, it's going to look at all of that information as it's gathered at runtime. So the processing takes the classes you saw and fills them in with the little templates for the things that you specified in a well-defined manner. Now, one particular trick here is how to handle frames in the language that's being interpreted. Normally when you build an interpreter, you make a structure, typically in your C, if you're doing it in a C interpreter, and you stick those things in the heap and you link them together, and that's how you implement the interpreted languages stack. And you do just the same here, but there's a trick. Your frames should be, when possible, virtual frames, which is another class that's provided by the framework. And a virtual frame, when you program it in Java, just looks like a Java object. But if you follow the rules with what you do with virtual frames, you don't store references to them in the heap, you don't let them escape from methods, then when the compiler comes to compile your interpreter, combined with the original AST, it's going to say, aha, this is a virtual frame. It can just become a frame on the stack. And it will optimize it all the way, pull out all of the constituent components and just stick those in registers or on the stack or wherever it thinks is the appropriate place. There are some other classes of frame. The most notable one is a materialized frame, which has exactly the same interface as virtual frame, but a little bit more. And materialized frames are real objects when they're when the program executes. So those are heap allocated, and you can convert from one to the other and back again using the API. But as soon as you're working with a materialized frame now, it's slower because it's an object. It's not just a stack frame. It's been optimized by the compiler. And then there's a thing called a frame descriptor, which is generated during the parsing, which sort of says how the frame is filled in from the source language. And that's what the system uses to do its optimization and de-optimization. One of the important things here is you never make these. You don't say new virtual frame anywhere. You always get them from the system, usually passed in as a parameter. You don't subclass them. You don't mess with them because the compiler has to know it's exactly what it thinks it is if it's going to optimize it. If it's off, then it's going to say, oh, don't know about those, can't do anything for you. I mentioned the root node. So the root node is important because it's the entry point for the evaluation of an AST. So you have to have some way of going from normal Java code into what looks like normal Java code, but when the truffle is running and compiling, it's not Java code anymore, it's machine code that's been generated by the partial evaluator. And so there's a transition there, and that's what root node provides you with, a way of making that transition. So when you have a root node, you can say to that, from the runtime, make a thing called a call target, and the call target is now just callable. You call it, and suddenly now you're executing in the interpreter associated with that node. You should implement this execute method, which is pass to virtual frame. You know, the system will make the virtual frame and pass it to you. But when you're compiled, it's really just a frame. How do you do control flow? Well, exactly the same as you would in a normal AST interpreter written in Java. So you implement it using Java control flow where you can, and where you can't, you use things like exceptions. And then what Graal is going to do, which is the underlying compiler, when it compiles an entire AST, if there's a throw and a catch point internal to the AST, it's just going to connect those with a jump. There'll be no actual exception object made. It won't do all of the wrapping, it'll just hand it with a control flow and the associated value from one to the other. So here's an example. This is how you might implement an if node. So an if node, you know, assume I have a statement node class. The if node has 3 children, one for the expression, one for the then part, one for the else part. And to execute this, this is of type return type void, because it doesn't return a result. I'm given the frame. I execute the condition part on the assumption it's going to return a Boolean. That's the way this language is defined. If it's true, then I call the then part. If it's false, then if there's an else part, I call that. Very straightforward, direct, so no messing about. When you want to invoke a function, then you have to pull out, say the function is the root of a tree, you have to pull out the call target from that node and call it. And you want to do that in 2 stages. The first is sort of building and binding the call target to the call side. So let's assume for the moment our language just has direct function calls. You see an F, it's calling an F. There's no dispatch in between. That's the simple case. We'll deal with the dispatch case later. So we've got an F and we want to call it. So we make a thing called a direct call node. Out of our root node, we pull out its call target, and we make a call node, direct call node out of that, and we keep it somewhere. When we want to call it, we need to evaluate the arguments to the call and then pass them to the thing in the call. So here's a common piece of code to do that argument evaluation. Let's start with the second line. So this isn't just normal Java. I'm making an object array with a length that matches the number of argument nodes in the call node that I'm in. So syntactically, you know, your call has some number of children for each of the arguments, and you know that length. Making an array of that and storing that in the variable arguments, and then I'm iterating over each of those things, each of those node trees. I'm executing as if I were interpreting that thing, calling execute generic, and the results going back in the array. And then I call the call node, passing in the frame that I had from outside and the argument array. A couple of things you want to do to make Truffle really know what you're trying to get at here is, firstly, assert for the compiler that this length is a constant through here, because then it will do a bit more optimization. And then if you say explode loop, which is I think you have to put before the method as an annotation, the compiler will see this loop and this constant and say, oh, I know exactly how many times I need to unroll this loop, and it will unroll it for you. So that all this actually doesn't become a loop, it just becomes direct evaluation of the children. They all get inline and pulled in. So there's no loop there in the end before it does the actual call invocation. Suppose you want to implement a return statement. Well, return has a, classical return has that non-local flow of control that's, you have to do something different in an AST interpreter. Then you do it using the obvious technique, using, what we saw weeks ago, using exceptions. So you build a subclass of control flow exception called, whatever you like, return exception that can box up your result. And when you execute the return node in a statement, all that does is throw that exception, stuffing the result in there. when it's handled, say in the evaluation of a function body, that will have the handler that catches the return exception and just returns from the function. In this case, it's just returning the value that was supplied in the return node. And as I said, when this is all processed at runtime by the compiler, all this code will just turn into a jump with a value in a register. Yes?
So you're talking about for the frames, there are not special ways of handling those. But if you're implementing your target language that has a language stack for its AST node definitions, is there any special way of doing
Don't do that. Okay. Do it in the straightforward way you would with an AST without doing. Don't build an explicit stack. Okay. Let's take a break. It's a good point to take a break, and then I'll go into some of the tricks for making this stuff run fast. A sense of the things that you have to write as input to Truffle. I'll talk a little bit now about what's actually going on under the hood and how you can guide that to generate good code. There isn't really time to cover everything you'll need to do a full Feeny, well, I'll get to that in a while, how we're going to phase it. One thing I didn't talk about though was if you imagine this specialization going on, imagine each of these circles is a method, and the arcs, the black and the red arc, those are all calls between methods, between ASTs. When we're interpreting, we're going to specialize these nodes to the types that we observe. But what happens in the case where we have a node, a method, AST, that's called from different places with different parameter types? Right. So in this case we have blue types, which might be integers. In this case we have string types, and this thing is some kind of generic method that can handle both cases. Well, the specialization, the downside of the specialization implemented naively would be that this guy would always be the generic case, because it would be specialized first for the first caller, and then it would get called by the other guy, and at that point it would go, I'm both, so I have to be generic. And that would be a performance problem. But in fact, what the framework does is, because it's counting calls in the profiling, it will detect the case where you have a frequent call. So the red here indicates this is much more frequent than the other one. So this is the hot one, calling something that's turned into a generic node. And it will take that AST and it will clone it unspecialized. So it will reset this guy to uninitialized. It will clone it over here as uninitialized and include it directly, some kind of private tree-inlined copy of the tree. And so this one now, when it calls it through this path, can do its own specialization without being polluted by the types that are coming through there. So this is, there are only a couple of things that are going on at the truffle level to do optimization, but this is an important one because it means that you can get type information that's specific to a particular call path through the graph, and that you're not blending in all of the types from all the other paths, even though they're very infrequent. Okay, so once you've got all this stuff, you get this big ball of Java code, and you can run it, as I said, on any VM. But if you run it on the Graal VM, that's basically a version of Hotspot with the Graal compiler in it. And Graal itself is written in Java, and it just runs as a Java program on the Graal VM. But Hotspot, about 2 years ago, was extended to have an open compiler interface. So basically what you can do is you can write a compiler in Java for Java, and if you register it through the interface, the VM will call your compiler to compile code, and your compiler can install code into Hotspot's code cache. Not something we want the average application programmer to do, but useful for this particular technique. So this compiler interface is, there's at least one compiler that mimics it, which is the which is the Graal compiler. Now, Hotspot still has its other compilers inside, and that's what's used to compile Graal when you start up. Because when you start running, you just have Java bytecode, and something has to compile that. It can't compile itself. So it has a couple of compilers, but you can add your own, and that's what we do. So your AST starts running. Hotspot's execution mechanisms are running the Java code in Truffle. The Java code has embedded counters, counting things. Eventually, one of those counters crosses a threshold, and it calls off to the side, and it says, oh, I want to be compiled now. And that's where Graal kicks in its Truffle mode. Graal can also just compile straight Java code. But in this case, you need kind of the extension that knows about truffle structure. And so Graal kicks in knowing it's a truffle compilation. And at that point it says, okay, I'm going to assume that the AST is stable, that you've been interpreting long enough that the types are stabilized, that everything is ready to have good code generated, with the penalty that if something changes later, we're going to have to de-optimize and regenerate code, and we'll interpret for a while to get the type information back again. So the thresholds are set such that this is likely to be true. So it will then start walking the AST and doing things like looking at the child fields in the nodes to understand the structure, looking for the execute methods that are in those tree nodes, and doing this aggressive inlining through the execute methods guided by the type structure of the AST. Also in the tree, there are counters and probability values for things like branches and type information for dispatches, which you can use to optimize and make decisions as to how it generates code. And some of these you can influence. You can put things in specifically to help guide the compilation. But by default, it does a sort of an okay job on the compilation. So the compiler inlines, super hyper aggressively through the tree structure, basically inlining everything it can. You might have to stop it from inlining it using various directives. We'll have some of those on the slide, because there are some things that, once you get into code which is extremely cold or bulky, you don't want that inline. You just want to call it, right? If you're calling, as I said, Java's print method, you don't want to inline print and all the internationalization tables and all of that stuff into, hello world. You want to just call that. So in certain places, it's useful to say, don't inline anymore here. Also, as you're writing the implementation of a particular operation, if you break it out into a branch with a fast path and a slow path, you can say, this is the fast path, inline through here. This is the slow path, don't inline through here. Or this is the slow path, don't even generate code here. Just de-optimize if you go down this path. And we'll see how to do that. So the compiler will take all that stuff, all those directives, all the tree, all the huge inlining it does, and then it does optimization on this massive tree structure that's resulting. So it's, by virtually inlining, all of the dispatch between the nodes is gone, because that's being done at compile time, right? The tree structure and the particular shape of the tree is dependent on your AST, and that's known at compile time. So that all disappears. The virtual frames all disappear and just become stack frames. And the exceptions, if they're within a compilation unit, all just disappear and become branches or de-optimizations, depending on the frequency. There is a tool that can help you see this, called Ideal Graph Visualizer. In the bibliography, I've got a pointer to a YouTube video where they use the IGV. This is kind of more for curiosity than anything. I hope you don't find you need this, because it takes a certain amount of practice to know what you're looking at from this. The tutorial is pretty good explaining it, but when you get into non-trivial examples, you'll have a screen this size looking at a tree that's, much bigger than your screen, and it will become daunting to wander through it. Unless you get experience with that, but hopefully you won't need to do that. Was there a question?
Yeah. The only performance downfall I can see if you're too aggressive in your inlining is blowing your instruction cache. How much problem is that actually in
Well, actually, if it gets too big, the compiler starts throwing up its hands and saying, because there are some parts of the compilation that I don't think are strictly linear, and at some point it will go, oh, this is too big, I can't handle this. I'll just give up, which is not good, because then you'll keep interpreting.
Also, blowing out your iCache is a problem. So, there was in one of the database Sigma, a while ago, there was a paper where they showed that iCache misses were the bottleneck on OLTP databases.
Oh, wow.
Because commercial ones. Because if you look at the ones you see in the university, they're maybe 10, 20,000 lines of code or something. And you look at a commercial one, it's 10 million lines of code. So
it's kind of one loop with
yeah,
a straight line through it.
right.
more
So
or less.
all the commercial ones that the iCache misses are the bottleneck.
Okay.
I don't think you'll get. I think the compilations will fail long before you reach that point. But that's also bad because it means you won't be compiling. You'll just be interpreting, and things will be very slow. Because your interpreter will be compiled by hotspot, but that's not the same thing as having the interpreter partially evaluated by Graal.
Right.
So your head can start hurting when you think of all the levels of compilation and interpretation here.
I am actually confused. So what level of compilation are we talking here? Graal is
So
taking
Graal is
to
taking your
bytecode.
AST and the bytecode of your interpreter and emitting machine code.
Oh, okay. So it's going from bytecode to machine code.
Yes. Yes. And it can do that for normal Java without an AST. So it's a vanilla Java bytecode, dynamic bytecode to machine code compiler. But in this mode, it also looks at the ASTs and the profile and type information in those ASTs to guide its inlining.
So this compilation is specific to the program that's running.
Yes,
The application.
exactly,
Okay.
exactly. It's compiling. What's happening here is it's compiling a fragment of a language it's never seen, right? That's the magic here, is that we have a compiler that's compiling something it doesn't know about Feeney. It's never going to know about Feeney. We're not going to put Feeney-specific optimizations in. But when it runs on your Feeney interpreter, it will be generating code for Feeney programs. Right. If we go back to the desiderata thing, the trick is where's the generate good code slide? That one. What it's doing is it's taking the semantics of each language element as expressed in your interpreter. It's taking the structure of your program as expressed in the AST. It's taking the hints from the profiling data and it's emitting machine code for a program in a language it's never seen before. That's the important difference here, right? We've got now a compiler which is reusable. It doesn't need to be customized for every language. The way you customize it is by supplying it with an interpreter. That's how it knows about the source language.
So if you look at this, if you look at this as a black box,
Yes.
and just see what the end result is, the machine code that's generated. Would you say it's similar to the way meta tracing works in that you have an AST interpreter and it's doing something, and this whole framework is trying to figure out what machine instructions it's doing for a particular program and generating
The high-level goal is exactly the same, which is to generate good code for a language that's implemented via an interpreter. The underlying mechanism, however, is completely different, which is why I wanted you to see both, because they're trying to do the same thing but via a completely different way. And you can make your own judgments when you look at the papers as to the effectiveness of one or the other, or which you like, or how it. It would have been nice if you could have written an interpreter and could processed it with PyPy as another exercise, but there are only so many weeks in the semester. It would have been very instructive, I think, to do it both ways, because I think you would have found very different characteristics in some respects. And we can talk about those maybe at the end after you've tried this, because it'll be interesting to see how well you do with this. This, I would say, is harder in that you need to know more, but in general, we're finding you get more performance out of it at the end. There doesn't seem to be quite so much of a performance barrier. But that's still, you know, both systems are in development, so that might not be the ultimate final story. Okay, yeah, that one. Already did that one. Okay, so don't do any of this until you've got it working before I go any further. Don't worry about this stuff. This is for when you start wanting to tune, and you're probably a couple of weeks away from that. But I'll cover them here because we've got no lecture next week. So these are the things that you can put in your code, which if you run your program on a stock JVM, they're all no-ops. Then they don't do anything. But when you run them on the Graal VM, each of them has a specific meaning. So if you annotate a field as compilation final, when the Graal compiler processes that AST node with that field, it's going to assume that field's never going to change thereafter and treat it as a final. So it can do optimizations based on the constancy of that value. If you want to write code that's never compiled, you put this call, there's obviously a thing before this, you know, truffle runtime or something you have to put before it, but this is the important thing. You put this call in your code, and when Graal sees this and gets to this point, it says, oh, just insert a deopt. Don't compile past this point, I'm just going to deopt at this point. So this is the way of saying, don't execute. If you use this call, it will not only deopt, but it will invalidate the code. So you put this in when you've come down a path that you never thought you were going to come down, and you've made decisions or assumptions, or you've gathered data which you now want to throw away and start again with a fresh compilation. This is basically the API for deopt, or one of them at least. And so this is done, for example, when you call replace on a node. This is the replace a node with one of a different specialization. That automatically invalidates any method that was generated based on the previous specialization. So that's why you want your AST to be stable at the point where Graal kicks in and compiles. Because if it isn't stable, the node switch will trigger this, and that will cause the deopt of any compiled code that's included that piece, that fragment. Truffle boundary I already mentioned. You can sprinkle that in various places, and that's kind of a hint that says, you know, probably don't inline through here. It's not. I'm not quite sure why they say it's a hint and not, you know, never inline through here, but that's what it's meant to mean. You can also test to see whether you're actually in compiled code or running in the interpreted version of the AST using this other test. And there's a cute use of that, which I'll show you in a couple of slides. So, when you want to profile, you can profile in a number of different directions. Simplest cases are about branches and branch directions. So if you have a test and you want to make an assumption that the code down one branch of that test is very unlikely to be executed, but you want to explicitly tell Graal this, then you can get one of these things called a branch profile, make a Java object and store it in a final field. And down some branch, if you enter that profile, then Graal will see that this thing is being called, and it will, in other compilations, it will probably have just optimized this code out and put a deopt there. So when the test passes, it will then deopt the code and recompile based on that. So that gives the system a hint on frequencies. There's a more nuanced version, which is called a condition profile, and that's for the case where you don't know what the probabilities are like. Right? It could be 50-50 or 60-40 or 90-10, but you just want to measure and have the compiler, based on the measurement it takes during interpretation, do whatever it thinks is the right thing. So you make one of these objects, and you pass it the Boolean that's the result of evaluating some other thing. And that increments counters for one, the true and the false case. And when the compiler comes back to compile this, it'll look at the probability is gathered, the counts of the directions taken, and take that into account as part of the compilation. So if it's 99 to 1, then it'll do an awful lot of optimization down the 99 branch, and down the 1 branch, nothing, or it might not even bother compiling there and play geops. So that's another way of gathering profile information that's useful. Here's a particularly, I think, sweet example, pulling some of these together. So this is the implementation of the condition profile that counts. Okay, so it has a counter for the number of times it was passed true, and a counter for the number of times it was passed false. Because remember, when you execute, you pass the result of the test to this counter. So it's going to count in true count plus plus and false count plus plus how many times value was true or false. But, let me come over here. Each of these is guarded by an interpreter, which means when this code is compiled, this code is completely elided. So the counters disappear when the inlining goes through this and inlines this method, because the counts are now in the interpreter only. Cleverer than that, though, if when you compiled it, the count was 0, remember this is compilation final, so now those numbers are never going to change. If when you compiled it, the true count was 0, and you made assumptions based on the true count being 0, if you come through this again, true count is gone, because that was a compilation final, but value is still there. It will say, oh, we've come down the true branch when we never, ever, ever came down there before. So, good time to throw away this code and start again, because we compiled on the assumption that this was never true, and in fact it's turned out to be true. So this causes the compilation unit to be discarded and interpretation to resume, and it will be recompiled again after some more profiling. You have to think about this one for a while. I'll let you stare at that. And then at the end, in the interpreter version, it just takes the true and the false counts and it stuffs a float in with a double with the actual probability of a true outcome based on the observation. It's a little bit mind-bending. Yes?
Do you see this stuff running into the same problem that like the register keyword in C has, or the inline, right? Like, why are you trusting the,
Yes.
or even why are you even encouraging
Absolutely.
them to use these?
This is not for end-user programmers.
Yeah, but
This
even
is for
the-
language
Yeah, but even
implementers.
for the language implementer, like, why can't, for instance, Graal just always profile everything?
Because it doesn't know where to profile. You don't want profiles at every single branch in your program. You want profiles that are tailored to the semantics of your language, and the only person who knows that is the person writing the interpreter. If they don't know that, don't mess with this, because like register, it can send you down absolutely the wrong path, which is why it's important to make it work first and worry about tuning later, and don't put these things in without gathering data. I'll talk about that a little bit later. This should all be done on a data-driven basis, sprinkling, but basically what you're doing is you're putting in declarative structures that shouldn't affect the correctness of your program, right? There's no way that this should change the behavior, it will only change the performance, and you're putting them in places where you think the compiler could use some help in making a decision. And if you can establish that, then you can put the thing in and it should do no harm, right? The worst it will do is make your interpreter a little bit slower. Yes?
So we're really when you're using the declarative directives to declare what children need to know.
So there's two uses of that. One is I'm implementing the language. I need certain different semantics for my operations. And the other is I know that I can implement a specific operation or a type using different representations with different performance characteristics. So if you were implementing, say, JavaScript, a naive implementation would use double as the one and only numeric type, because that's what JavaScript has as its one and only numeric type. That's the language semantics. All numbers are doubles. And you could implement it that way and it would run just fine. But if you put an additional specialization in that says, in the case where I've seen only ints, I'm going to represent things using an int or a long, and I'm going to re-specialize when I see an actual fraction appear, then it will go faster because it will generate integer-only code in the places where those operations are used that only use integers. So there's kind of two different functions for the specializations. Capturing the actual semantics and then specializing additionally to capture particular cases that you want handled specially. Again, it's a good idea just to start with the first kind and put the second kind in later, because you can always add specializations later. Any other questions on this? Okay. The most general form of dependency is encapsulated in this class assumption. Remember when we talked about dynamic compilation and de-optimization, I talked about a dependency graph that registered compiler optimization decisions that had been made based on some assumption in the compiled code. Like I showed you this in Self, where I could make an assumption about, say, the types of say the plus. Plus is going to be ints. I've only ever seen ints. I'm going to inline int plus. But when I change the int plus definition, I have to find all of the places where I made that decision and throw that code away. Well, this is an API for doing exactly that, without having to implement all the machinery under the cover. So in this case, what you do is you create an instance of this thing called assumption. And in your code, in the interpreter, you can check an assumption in a straightforward way by doing assumption.check. And if this code is true, then the compiled code after it is valid and it will run. But if somewhere else you say assumption.invalidate, the runtime system will find all the places that you did this and it will throw away the code where this was inlined. So this check disappears. It's not in the compiled code, right? Because the code is assuming that that's true. The check is made, down here, and the result is to throw away the code on which the check is based. So there is no performance penalty for including these things on the true path. So this is used in a number of different places. For example, if you have a function, you have a language in which you have a function and you can redefine functions, you can have a call that calls a function and the function will be inlined, but you want that code to be discarded if the function is redefined. Functions are redefined usually infrequently, so it's usually the right thing to do to inline it and discard the code on the redefinition. And you can use this mechanism to do that. There's a particularly sweet example of this in the Ruby implementation that's been done on this. In Ruby, you can redefine very, very basic primitive things like a plus. And so you can be evaluating a plus on a couple of integers. And in the left child of the plus can get redefined. And the plus operation is supposed to use the redefinition. Right? Now, if we were to compile that without this mechanism, every time you compile plus, you'd have to check whether plus has been redefined. And in fact, that's what JRuby does. It has a global flag that says, I've redefined plus, and it just throws all that stuff away. And now you're running slowly through all the slow pluses where everybody is checking. But in our system, you put one of these assumptions in, and when plus gets redefined, only the places that use plus get de-optimized, and they can be re-optimized using the new definition later if you really want.
So to clarify, it doesn't happen when you call invalidate, only when an exception is there.
Yeah, because this guy, so assume you're running this code and something invalidates, we're going to call this invalidation, right? And that's going to throw away this code and anything that it was inlined into. So this code here now, which assumed the assumption was true, is not going to run anymore.
So, is there any restriction in the way in which assumption objects can be used? Or how does Graal track invalid? If assumption.check is
When it
not-
compiles this, it'll put in the dependency from this to this. So that when you call this code gets discarded, or any inline version of this code. That's all it's doing.
But the variable assumption could refer to more than one assumption object, and you could have an arbitrary number of objects that you.
Well, no, it's one variable.
Okay. No, I mean.
You have to send check to an assumption, and assumption is an instance of assumption.
Right,
I'm not sure I follow where.
At compile time, you're not really sure whether the assumption that is being invalidated over there, the same assumption that's being checked over there, right?
Well, but
They
they
could
are
change.
because they're in the same variable, right? And I think this should probably be a final,
Okay, so that's
Okay.
probably what.
or a compilation final, or something like that. Right. But then, it's a reference to an underlying object somewhere. Okay. I've elided a lot of decoration from these to get to the point. So, I think I already said that. Okay. There's an object system in which you can build objects. I'm not going to go into this mainly because I don't understand it fully myself yet. But basically, there's this thing called dynamic object, which looks like a Java object. It actually looks more like a Java hash map with keys and values. And you use it in implementing objects with random structure where the properties can come and go. But behind that, there's also other structures called shapes, and a shape captures the particular usage of one of these dynamic objects with particular sets of keys and types on their values. If you use dynamic objects in your guest language, and as in most guest languages, they change structure in relatively infrequent and well-defined ways. You run something, you add an X here and you add a Y there, and mostly the X's and the Y's are referring to ints or doubles, things like that. Then the compiler can track the use of these shapes and optimize the cases based on the actual shapes that are extant in your program. So you end up with something that looks like a hash map implementation of an object, but actually gets implemented down to the conventional kind of struct implementation of an object with offsets and direct lookups. You'll need this when you come to do objects in Feeney, but I need to get you more tutorial material to do that yet, which I wasn't quite ready. So, but the exercise will be broken into two parts. So you're going to start by implementing the basic values and functions in Feeney and control structures, but without doing arrays and objects and methods, because that adds a fair amount of complexity. It will take some time for you to get into the mindset of using this system. It's not like writing an interpreter in C. Not very much like it at all. And in fact, the more your program looks like an interpreter in C, the worse it's going to perform in the long run. Because the one thing that Graal won't do is do magic optimization on arbitrary Java code. It needs the structure to understand what you're doing. And if you just have sort of Java stuff, it's just Java. It's not going to run any faster than that. So in step one, the exercise, which we'll hopefully put together by the beginning of next week, you'll be doing functions and control structures. And then step two, if you're feeling brave, you can try it all at once. I mean, I don't really care whether you break it up or not, but I would advise starting small. And you'll be programming in Java. You'll probably want to use an IDE of some kind. So it's quite different set of infrastructure than what you've been using so far. In the bibliography, you will find a bunch of resources that will help you in this path. I would recommend reading the paper on the truffle DSL that was published a couple of years ago. Unfortunately, the details of the language have changed since that paper was published, so don't take the examples literally. There is a pointer to some stuff on the web which explains some of the differences. Hopefully the basics and the gist of the paper will be not misleading. There are also other tutorial slide sets and sample code that you can look at for guidance. In particular, there is in the repository, which everyone will have as part of their setup, an implementation of a language called Simple Language, which in fact is actually, I think, more complex than Feeney by quite a bit. So Feeney is even simpler than Simple Language. And you can look in there to get hints as to how to structure things and examples which both work and are reasonably well commented. So it's explained in the code. There's a tutorial. Actually, there are several tutorials, in YouTube with slides and video. Because the system is a moving target, the further back you look, the less accurate the tutorial material is, because the system's evolving. And so something 2 years old is just going to have stuff in it which isn't correct anymore. So I would go for the most recent ones if you can. But the code in Simple Language is known to work. So that's sort of the rock on which you should anchor things. How do you do this? Well, like I say, don't think of this as writing an AST interpreter in C, just translate it into Java with the odd @ sign here and there. That's not what you want. What you want to do is you want to take each of the nodes, build a node hierarchy, define your types, and then start putting in the specializations which will guide the code generation. Look in Simple Language, for example, but the code that I've had on the slide is all basically derived from the Simple Language example, so it shouldn't mislead you. If you see complex control flow in a node, particularly that's testing on types, that's a hint that you should be specializing into those types and letting the DSL select between the alternatives. You shouldn't have instance ofs in your code, broadly speaking. That should all be in the framework guided by the type declarations that you put in. Don't do any specialization in parsing. I don't think you'll have a parser supplied to you anyway, so I don't think you can. Just trust in the runtime stuff. Then if you get to the stage where it's working and you want to tune it, once you get there, the tuning hints are don't try to speed up the interpreter. That's the wrong approach here, because the interpreters are only going to run for a few thousand iterations. What you're looking for is to give hints that the compiler can take and generate really good optimized code. And it'll be like 100x faster than the interpreter when it compiles. But you have to get it to the point where it does compile, and you want to guide it to compile the right thing in the right way. So the trick then is put in the profiling information that it needs. You'll have the type information already there by virtue of the specializations, and it will use that. If you find representations that are even more optimized and you can add specializations for those, that will help too. And then you can put in profiles like the branch profiles and the condition profiles and stuff like that to guide compilation and to measure in the places that are key. I would use micro benchmarks. While you're implementing a language feature, write little micro benchmarks for the variance of that feature and the variance of the type, and time them. Maybe even look at the code that's generated and see where, or the GRAL and the IGV. That's the way people who are really building languages do stuff. They look in IGV to see where the stuff gets optimized away, and then they put in the appropriate specializations and profiling. I'm guessing you won't have time to go quite that far though. You want to use final fields where possible, because final is a great way of telling the compiler this isn't changing, and it can do a lot with that. And if the Java final is too restrictive, then compilation final can be used instead. Take 10 minutes, and I'll tell you about system architecture. And I'll call this guy. Okay, 10 minutes.
Same here for the service.
Stuff with the system. I want to just describe some of the things that we're doing with it, and hopefully motivate why you're even bothering with this stuff. So the architecture of the system is broadly, as I described earlier. We have this truffle framework, which is a pile of Java code and an annotation processor. and language implementations that sit on top of that, and all of that stuff is pure Java, and it can run on stock JVM, but with not good performance. When you replace JVM with a Graal system, which is the combination of the Graal compiler and the hotspot JVM and the compiler interface, you then get to run this stuff with pretty good performance, and it will run anywhere that hotspot runs because it's using the production version of hotspot. And we currently have these languages in a fairly advanced state. There are various other languages that I'll list at the end that are in a lesser advanced state, but we're progressing forward with them. And we've open sourced much of the system, certainly enough that you can build languages and experiment with the system. We also have a replacement for hotspot that can sit down here, because when we write these languages and the framework and the compiler, we actually restrict ourselves to a subset of hotspot of Java, which firstly relies on a closed world assumption. We don't do any dynamic class loading or anything like that ever in any of these implementations. And we also don't use reflection at runtime. And so what we can do is take all of these things, process them statically, tree shaking, elimination, all of that stuff. And then once you've done all of that and eliminated all of the stuff you don't need, you can run them on a VM which implements a much smaller subset of Java that doesn't have all of the mechanisms for dynamic class loading and reflection and many other features. And that, as a consequence, is much smaller, starts up more quickly, has better footprint. And by the time you've done all the tree shaking up here, you've eliminated a lot of the overhead in your system. That tool is also designed to be embeddable within larger systems. One of the difficulties with trying to embed something like hotspot is it tends to assume it's in charge of a lot of global properties within the process it's running, and it takes over signal handlers and things like that. If you have a thing you want to embed it in and it has its own definitions of signal handlers for the same signals, you get these horrible conflicts and memory management and all of that stuff. This doesn't have any of those problems. It's designed to be embeddable. In particular, given the nature of Oracle, there are a couple of obvious places where you might want to put it. And that is indeed where we're trying to put it. So we think, we hope, we hypothesize that maybe we've resolved this complex thing, that instead of doing all of that, you can write a parser, you build an AST interpreter, you have something that works, it's okay, and then you tune your specializations and your declarations and all of that stuff, and you end up with something that's already pretty fast. And instead of having to go through all of this pain, we are the ones who've gone through this pain, and you get to leverage all of that stuff that's been pushed into all of the tools and the tool chain and the VM. As I said, we're quite well advanced on JavaScript, Ruby, and R. C, of all things, is underway, and I'll explain that in a slide or two. We just started doing Java, which means Java executing by truffle interpretation and not by bytecode interpretation. And we're also working on a front end for the system which can inject LLVM bitcode into the system, so we can take bitcode from languages that have LLVM front ends and run that too. That's just begun, so we have nothing really to show for that. There are other groups who've tried various other experiments. There was an experimental Python implementation done at Irvine. I don't think that's actively under development yet because the student graduated, but he got a fair way with Python, but mostly the language core, it's quite a big amount of thing to make a full Python implementation. There's a fairly advanced Smalltalk implementation, and there have been some experiments done with Scala too. You can find all of these mentioned in the literature in the bibliography. For performance metrics, I'm going to give you a couple of slides. These slides are out of date, so they don't capture the exact reality of the world, but use them as a flavor of where things are. And in the case of Ruby, the implementation's incomplete, so it's hard to make performance claims when you haven't done the whole language, because you might have cheated. But I'll try and explain why we don't think we've cheated. So this is some numbers from our JavaScript implementation compared with Google V8. Numbers, I think, come from early summer, so they'll be out. Something will have changed by now. These are running the V8 benchmarks, so their benchmarks, not our benchmarks. And you can see ballpark, it's competitive with V8. It's in the same region, a little bit up in some places and a little bit down in others. But we're getting approximately Now, the other thing I should point out is this is peak performance, not at the startup it's terrible and it needs fixing, and there are some other things that need fixing. But it is a complete implementation. It passes 100% of the ECMAScript JavaScript test suite. So it's a complete implementation by any reasonable definition. This one shows some of the work we're doing on Ruby. So this is an image processing library that was built by somebody external to do kind of Photoshop-like processing on images in Ruby. When you run it on the C Ruby interpreter, that's normalized to 1. When you run it on our Graal Ruby interpreter, it's 8 times faster. Now, the person who wrote this was so unhappy with the performance on the C Ruby interpreter that they rewrote the kernels in C. And when you run the combined version that they have, which has the outer parts in Ruby and the inner parts in C, it's 11 times faster than the original. But we have the C implementation as well, where we, of all things, interpret CASTs, and then we can code generate and inline those into other languages. And when we do that, our implementation with the C code being fed through Graal is now 3 times faster than their implementation with the C code being fed through GCC. And the difference here is because we're using a common IR for compilation for both languages, we can inline across that boundary, where a normal system, C compiler generates C code, machine code for the C part, the Ruby system is interpreted and is compiled separately, and that boundary is a very expensive boundary otherwise. So we eliminate the overhead of that boundary significantly. We're now doing a lot of work on multiple languages and interoperation between those languages so that you can write a relatively fine-grained expressions, methods, loops with the inner part of the loop calling to one language and the outer part in some other language, because we think that might be a very interesting direction to go in. And this particular experiment is described on Chris Seaton's blog page. The C implementation, when you run kind of standard C benchmarks through it, it's within about 25% of GCC with all the optimizations turned on, so it's not a bad C compiler. So, back to the original picture. This is how things stood. This is what we want to do. We want to get everything down into this band. I think it's unrealistic that some of these languages will ever be as fast as C, partly because semantically they do more work. They have to maintain safety. C doesn't. And semantically they have to maintain some level of flexibility, like redefinition, which isn't there in C. And so you're always going to pay some penalty for that. But the hope is that the penalty is, at most small integer multiples, not factors of 10. And we're trying to get down to this level. So we're sort of there with JavaScript and Ruby. The R implementation is still a ways off, but R takes a lot to implement, but we're getting there. And then the nice thing is, because we have one system for all of these languages, we can optimize in between them in a way that hasn't been possible before. The substrate VM part, then, last thing I'll mention, takes the language you specified, the JDK, and the substrate VM definition, does a bunch. We use Graal as a static compiler as well to do ahead of time compilation of that whole stack, and tree shaking to eliminate all the parts that aren't used, and then we can generate a conventional binary for the resulting VM that doesn't need hotspot, it just runs your language directly. And this is typically starts up in milliseconds rather than the whole normal stack, as you'll see when you run it, is about a second in startup time. And it's often, the minimal hello world is like 2 orders of magnitude smaller than, as you would expect, hotspot plus a whole bunch of Java code is going to be a lot of memory. It's going to be many, many megabytes. This can be down to hundreds of kilobytes in contrast. So I stole some of this stuff from Christian's tutorial. I recommend you go look there, and to give you some idea of how many people have worked on this, there's the eye chart, and I will close at that point. Any more questions? If not, we'll finish a little early. Yes?
Is the substrate VM also something that's available?
Not yet. It's not finished yet. If you want to work on it, however, we are looking for interns.
For languages whose semantics can be expressed more or less nicely using the JVM bytecode set, how do you imagine those would perform against the truffle methodology?
So I think JRuby is a good indicator in that JRuby can be expressed, but not nicely, because it's a dynamic language. And I think all dynamic languages are going to fall afoul of the same problems that JRuby had. And we're seeing 5 to 10x speed up over JRuby. And I would expect the same for Python and R and JavaScript and all of those others. If you look at, say, the JavaScript that runs on the JVM, there's Rhino and Nashorn. We're considerably faster than both of those. Much faster than Rhino, because that's an earlier thing that doesn't attempt to do anything fancy for the JVM. Nashorn does a little bit more work to try and get speed out of the JVM, but we're still, many integer multiples above Nashorn.
Wow. Okay.
Which is sort of what you'd expect. If you can compile out all of the overhead, you should be getting down to something that you'd expect out of a C compiler with the extra checks that can't be removed for safety. If you actually go look at the one of the tutorials I found was particularly useful is a tutorial given by Thomas Vertinger, which I mentioned in the bibliography. Partway through that, he takes the simple language example of just running a loop, and he looks at the machine code that's generated for it. And it's pretty good machine code, right? You have an overflow check that wouldn't be there in C because it all spills out to begin arithmetic on the case of overflow. But if you had defined a language that didn't do that, it wouldn't put that in either. So, yeah.
Actually, that's my second question. I'm not really a processor guy, but
You're not, sorry?
I'm not a processor
Okay.
architect, but these extra checks, when you run them on an out-of-order processor, what is the additional penalty that you get? I imagine they all run in parallel out of line.
I mean, there's a price to all of these things. They're not completely free. They're not expensive, but they're not completely free. And certainly, I think it's a reasonable assumption that the runtime of your program is roughly proportional to the path length of the machine code you run.
Patrick, it'll still reduce throughput because then it has to do the check instead of doing something else, even in out of order for.
Okay.
Right.
Okay. All right, so I'll see you in 2 weeks. And good luck with your exercise.